So we're going to differentiate some trig functions today. So as you know, and we've done this for many other graphs, we can find the derivative of trigonometric functions by graphing their gradient function. So remember, when the gradient's 0, the derivative 0, that's where it crosses the axis. When it's positive, it's above the x-axis. When it's negative, it's below the x-axis. So the first graph I've got is sine x of x. Now next door are actually drawing this themselves, but we're going to do it as a collective group because I wanted to do the PowerPoint. Okay, so the gradient at the point 0, it's positive, is it negative, what is it? Okay, oh, I'll make it red because red's easier to see, I think. So it's positive, 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 0. Then it's neg, 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 0. Pause, 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 pause. Yep. So we start positive. We cross. Oh. We cross at 0 here. We cross at 0 here. So we're positive here. Then we're negative. Then we're positive. Does anyone know what that's a graph of? Oh, yes! It's cos. So, when I differentiate sine, I get cos. Oh, did you look ahead? Oh, you looked ahead, didn't you? It's kind of hard because we haven't looked at trig graphs, and then we're, yeah. But anyway, so if we have cos x, what's the gradient here? Neg, 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 neg. 0. Pause, 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 pause. 0. So, at pi, we're crossing 0. At 2 pi, we're crossing 0. Wait. Yep. 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 Oh, because this is where my gradient is. Oh, there should be a 0 there too. Thank you. And there. So, we're negative. Then we're positive. Then we're 0 again. What does that look like? Well, this was sine. This is negative sine. Woo! Okay, 10. 10 is stupid. And I don't like doing it with the graph because it's a bit crazy. It's super crazy. I'm not sketching that. Stuff that. I'm telling you it's sec squared. Okay. Yeah, I'll Google it for you because I'm not drawing that. Because, like, it's got asymptotes. You know, they go up to infinity and it's just like, oh, we're super big now. And then suddenly we're super small. Where are we? There's Mars. So, I'll put them on the same axes so you can see them. Y equals 10x and y equals sec squared x. Okay? So, you can see why I didn't want to graph it. So, that one's not as easy for me to look at and be like, yeah, see, that's what it looks like. But if it's crazy, we know it. Yeah, so that one's actually easier using quotient rule with sine and cos. So I'll show you that. So, because we know tan x is sine x on cos x. So if I was to differentiate this, we have, what is it? U is sine x and V would be cos x. You'd end up with U dash is cos x, V dash is negative sine x. You know what? I wrote it here. So here, if you derive them using product rule, you get cos x minus negative sin x, which is cos squared plus sine squared x, which we know is 1, yes, over cos squared. 1 on cos squared is sec squared. Wild, right? Anyway, that's it algebraically. You don't have to derive these, you just have to know what they are, and they actually are on your standard integrals page. Well, I think that is snipped from your formula sheet, but I'll double check that. So if we differentiate sine, we get cos. If we differentiate cos, we get negative sine. If we differentiate tan, we get sec squared. Okay? So just like when we did log, do you remember when we did log, when we differentiated log, we had to differentiate what was inside the brackets, stuff like that. We're basically going to use chain rule to do most of these. Okay, so we're going to differentiate what's in f of x, that will come out the front, the derivative of that, and then we just write sine of the function or cos of the function, etc. So, example here, if I was to differentiate sine x, I'd differentiate the 5x, so if f of x equals 5x, then f dash of x equals 5. So the 5 comes out the front, and I'd write, cos of 5x. That's it, done. Okay? We cool with that? So you differentiate what's inside the brackets, bring it out the front, and write differentiating sine is cos, so it'd be cos of 5x. So here, differentiate sine x in degrees. Now, we cannot differentiate in degrees. We have to differentiate in radians. Okay, so first thing I need to do is change it to radians. So I actually have y equals sine of x times 180. Yes. Pi over 180. So times pi. It's divided by 180 times pi. Yeah? Okay, so we have our degrees over 180 times pi. Yeah? So that's the same as sine of pi x over 180. Yes? So when I differentiate this, if I differentiate inside the brackets in respect to x, so pi x over 180. Now remember, pi and 180 are just numbers. So just like when I had the 5x, what will be when I differentiate this? Anyone? It's got pi in it, yeah. Yeah, it's just pi over 180, because that x would come down a power to the power of 0. We're differentiating in respect to x, so pi and 180 are just numbers. Yeah. So then we'd have pi and 180. The differentiation of sine, once again, is cos of pi x over 180. So we'd end up with y dash equals pi over 180 cos x.
Because the differentiation of the sine
in degrees. Yeah.
and so
because that's what x is, that x degrees is that. Yeah, so I put the little degrees sign back on it. But you just got to know you got to change it to radians. So here, find the exact value of the gradient of the tangent to the curve of y equals x squared sine x at the point where x equals this. So we know that we mean, oh, it just says find the exact value of the gradient of the tangent. So I don't need to put it in point gradient formula afterwards. So that's nice. So we have a product rule here. So u equals x squared, v equals sine x. So u dash is 2x, v dash is, yep. So product rule is, so that will be 2x sine x plus x squared cos x. Yeah? And all I need to then do is put pi on 4 in there. So 2 times pi on 4 sine of pi on 4 plus pi on 4 all squared. Yeah, it is. It's 45. So they're both 1 on root 2. So that would equal 2 pi on 4 is just pi on 2. And sine of pi on 4 is 1 on root 2. Can we draw the triangle up? Anyway, there it is. Plus, that squared is pi squared on 16 times cos of that is 1 on root 2. And we'd keep evaluating this, so that is...
You have to rationalize the denominator that one first thing.
I'm just going to simplify it first. And then I'm going to cross multiply because the root 2's will actually rationalize it for me when I add them together. So that's pi squared over 16 root 2. So here when I cross multiply, Bridget, when I multiply these by each other, the root 2's are going to disappear and become 2. Yeah? So when we cross multiply, we'd end up with 16 root 2 pi plus 2 root 2 pi squared. How ugly. This is ugly. Over 32 times 2 is 64. Because 2 times 16 is 32. Root 2 times root 2 is 2. So then I'd end up with 32 times 2. Okay. Yeah, that's ugly as, isn't it? Yeah, I'll just leave it like that. That'll do. I hate having roots and pies and... Anyway. I'm going to take the root 2 out the front. It's annoying me. So root 2 of 16 pi. Yeah, but I could also take the pies out, but I don't like them next to each other. This is just me being like, ugh, why are you so ugly? Oh, no! You're right. We could simplify that. Because 2's will cancel the 64 into 32. Wait, yeah. 32 root 2, 8 pi plus pi squared. That'll do. That way the root 2's not in there and it's not frazzling me. So I hate it. Huh? Because I just don't like write root 2's next to pies. Like, you could take the pies out, but I just don't like writing them next to each other. I think that's just like a weird... Yeah, no, that just means I'd have to cancel out the 2's. But yeah, I just don't like them next to each other. They just... I just don't like it. I really don't like it. Like, you can like it. Like, that's still right. But yeah, I don't like writing them next to each other. If I can avoid it. Yes. Yes.